as I mentioned yesterday, it's not a coincidence that those coefficients in Pascal's triangle turn out to be the same as what we saw in combination. So as we know, we can calculate those without Pascal's triangle using the formula n factorial on k factorial n minus k factorial. Of course, you have a button on your calculator that will work that out for you. But some of these questions we will need to go back to the actual definition to go and solve it. So let's actually prove it. Couldn't prove it last year because when we first saw it, it was back in term 1. But now that we've seen induction, we can prove this to be true. So first step is actually going to be for k equals 0 because the first term is NC0. And we have in our Pascal triangle relationships stated that NC0 was equal to NCN is always equal to 1. So left-hand side, NC0, that's equal to 1. Right-hand side, if I put it into our formula there, n factorial on 0 factorial n factorial, and again remembering 0 factorial is defined to be 1, then that also turns out then n factorial, which cancels 1. So is true for our first case of k equals 0. Okay, so I'm now going to assume it's true where k equals r. So I'm going to assume that NCR is in fact n factorial on r factorial n minus r factorial. We're going to prove it true for r plus 1. So what I'm attempting to prove is NCR plus 1 is n factorial on r plus 1 factorial n minus r minus 1 all factorial. Okay, how am I going to prove that? Well, again, you say we had our Pascal's triangle relationship that said any particular number in the triangle, I can go to the row above it and add the two terms above it. So n plus 1 CR plus 1 will be NCR plus NCR plus 1. Well, it's NCR plus 1 that I'm trying to find here. So if I rearrange that, I'll get n plus 1 CR plus 1 minus NCR. But we have assumed that NCR is n factorial on r factorial n minus r factorial, which also allows me to assume n plus 1 CR plus 1 factorial is n plus 1 factorial on r plus 1 factorial n minus r factorial, because all I'm really doing is replacing the r with the r plus 1 and the n with the n plus 1. Let's play around with that. So n plus 1 factorial, get a common denominator, and the common denominator, well, r factorial would be in r plus 1 factorial, so that would be the greater number. N minus r is common in both. So what's different? The denominator is the same in the first one, so I've just got n plus 1 factorial. In the second one, I must have multiplied it by just r plus 1, not r plus 1 factorial. Let's tidy the top up then. Common factor of n factorial. If I take n factorial outside of n plus 1 factorial, I'm left with n plus 1. And then minus all of the r plus 1, so I get n plus 1 minus r minus 1. So that then tidies up to be simply n minus r on the top. And is that what we were trying to get to? No, not quite there yet, is it? Now the n minus r will cancel in the n minus r factorial. What will it leave me with? It's got to be n minus r minus 1. It's like saying I've got 5 on 5 factorial. Well, if I cancel the 5s, I'd be left with 4 factorial, 1 less. So I'll be 1 less than the n minus r. I'll have the n minus r minus 1 factorial. That is what we were trying to prove. And so hence the result's true, and so on, and so on, and true for all positive integers by induction. So okay, so there's a proof of our relationship that we saw way back in term 1 last year. Well, let's get on to what the binomial theorem actually is. That's it. The binomial theorem is really just for 1 plus x to the power of n. And so you get NC0, NC1x, and so as we saw, powers of x are going up by 1, and we have our binomial coefficients. Of course, that's very limited in its use. Oh, in some notation, we could write that as the sum from k equals 0 to n, and the general term would be nck x to the power of k. So it is like a series. And nck is defined, as we just saw, n factorial on k factorial, n minus k factorial. And there will always be one more term than the power. Because if you think about it, if you expand out a perfect square, you end up with 3 terms. Expand out the cubic, you get 4 terms. There's always one more. And that's because we're starting at nc naught. We're going from naught up to n. As I say, that's very limited in its use. So if I replace 1 with a and x with b, I can come up with one which will cover every binomial situation. So the difference is, of course, we now have a in there, and it will start at the highest power and will go down by 1 each time. But the 2 powers will always add up to be n. Now, the order that those terms are written becomes important, because if they were to say to you, what is the 4th term, whilst a plus b to the power of n is the same as b plus a to the power of n, it will give us a different 4th term. So you need to do it in the order that they've expressed. So you start with the 1st term to the power of n going down by 1, and then the 2nd term will be going up. Evaluate 11C4 without your calculator. You would go back to the actual definition. This is how we used to do it in the good old days. We didn't worry about calculators. No, we had the calculators, but we'd actually break it down to factorials, and it's quite quick, because the 7 factorial will actually go into the 11 factorial, leaving the 11 times 10 times 9 times 8 on the top. And you will always get cancelling, nice even cancelling, because I could say, well, 4 2s are 8. 4 2s are 8, that cancels. And then now all I've got left on the bottom is 3. Well, 3 will go into 9, leave me with 3. So it's just 11 times 10 times 3, 330. Now, you need to know how to do that. Mind you, the ones we'll see, they won't be actual numbers. It'll be algebra that will be cancelling. Find the values of n so that NC5 equals NC8. Well, this is using the idea of the symmetry of Pascal's triangle. So which row would have the 5th one equal to the 8th one? Well, NCK is equal to NCn minus k. That's the actual relationship. So if k is 5, n minus k is 8, then we can work out n is 13. Basically, add the 2 numbers together. So again, it's that idea, the 2 numbers should add up to be n. NC7 plus NC8 is 20C8. Well, this is using the idea of, to get any particular number, we add the 2 immediately above it. So it's using n minus 1 ck plus n minus 1 ck minus 1 is nck. So in this case, n must be 19. The row above it would have been the 19th row. So this is what I say, we've got to make sure we get the terms in the right order, because they want the 5th term in this expansion. I start out with this. Rather than writing the whole expansion out, which would be a waste of time, I just write the general term down. So the general term will be, it's to the power of 11, so it'll be 11ck. The 1st term will be to the power of n minus k, in this case 11 minus k. And the 2nd term, which is negative 3 on b, will be to the power of k. Actually, the reality is when I write it, is I put the power of k on there first, and then I always just say to myself, oh, it got, in this case, add up to be 11, so therefore the other power must be 11 minus k. Notice, though, that is term k plus 1, because the 1st term is when n equals 0. So if you sub in n equals 0, you'll get term 1. Okay. Now, we want the 5th term. So the 5th term will be when k is equal to 4, not when k is equal to 5. So if we sub in 4, I get 11c4, 5a to the power of 7, negative 3 on b to the power of 4. So I know it's going to be positive, because a negative number to the power of 4 would be a positive number. Well, that would be unsimplified answer, which is quite fine in a lot of these questions, because the actual number there is going to be huge. 11C4 times 5 to the power of 7 times 3 to the power of 4 would be a very big number. So a lot of times it's quite okay to leave it as the unsimplified answer. But the actual answer, if you did want to work it out, there you go, 330 times 78,125 times another 81. Big number. Oh, what is that? Ah, it's too big. But anyway, large number. Going to find the particular term that's independent of x. Well, independent of x is just another way of saying we want x to the power of 0. Because if x to the power of 0, it would be 1. The x would disappear. So once again, I'll start with the general term. So now each term will be in the form, in this case, 9ck. The second term, so negative 1 on 2x will be to the power of k. So therefore, 3x squared will be to the power of 9 minus k. I basically need to work out what k is going to be for this to be independent. So I don't really need to worry about the coefficients at this stage. I just need to look at the x's. And so x squared would be to the power of 9 minus k. And, well, x is on the bottom of the fraction here, so x to the power of negative 1 would be to the power of k. And we're saying when would that all work out to be x to the power of 0? So don't worry about the numbers. We can work those out later. So the powers, well, square it, so that power becomes 18 minus 2k. The second one's negative k. Add the powers. We end up with k has to be 6 for this one. So now I can go back and substitute in and work out what the actual term is. So 9c6, 3x squared cubed, minus 1 on 2x, the power of 6. Well, we know the x's are going to disappear anyway. So I get 9c6, 3 cubed, over 2 to the power of 6. Again, that would be the unsimplified answer. 5D, we'll have a bit of a play around with the general term of the binomials and working out different terms.